Alrighty. Kind of a small crowd today, but I think we'll probably get a few more people trickling in here over the next few minutes. It is time to go ahead and get started, though. As usual, just kind of start off with a quick check in with where we're at in regards to the class. We got our third homework assignment coming up later on this week, but as I've said at least a few times now, if you need some extra time on the weekend to put some finishing touches on the assignment, that is totally fine with me. Just keep in mind we do have that final homework assignment coming up, which is actually what I'm going to be talking about towards the end of class today. So that is our last homework assignment. We're kind of at the home stretch here, but we do have somewhat busy couple of weeks with the final round of presentations coming up, and then our second exam and the last homework assignment. I believe, well, I know actually, everybody is signed up for a presentation date. There are still some people who haven't taken papers yet, which isn't really that big of a deal, but I would like that to be done sooner rather than later. So if you haven't picked a paper yet, please make sure, well, please make sure to take a few moments. Multiple people have gone off the list that I posted this time, which I think is fantastic. I'm really excited to well, I'm excited to see all the presentations, but also excited to see some new papers that I haven't really seen that much as well. So feel free to do that if the available papers on the website aren't really interesting you. You're always welcome to go off script a little bit. That's totally fine with me. I don't think there's really anything else that I need to address logistic wise at this particular moment in time. So unless anybody else has questions about what's coming up, I'm going to hop right on into today's material. So this day has been kind of a long time coming. We're actually going to be talking all about MPI today, which is sort of the king of parallel programming in the high performance computing world. I promise you that all of the machines, big machines on the top 500 list that we've been talking about all summer long are using MPI. A good number of them are using OpenMP as well. In fact, we'll kind of talk about that today a little bit too, since we've already played around with OpenMP and are kind of familiar with it. But MPI is by far the most widely used parallel framework within high performance computing. So there's no way we're going to go through a high performance computing class without talking about MPI. We're going to go through a lot of examples today. The fourth homework assignment is written with MPI, so we're going to spend some time talking about that towards the end of class today. And yeah, let's go ahead and hop right on in. So we are now in distributed memory world, the distributed memory paradigm. So recall that before, when we were using pthreads and OpenMP, we were in the shared memory programming paradigm. So that means that all of the processes, all of the threads, we're able to communicate just by reading and writing to the same locally accessible memory. Whereas with distributed memory, that is no longer the case. We now have a chunk of memory that is not in one place, but is now spread out across many different nodes, typically. So where one node can have more than one core on it, so we can do parallelism within a node, of course, but to really maximize, really leverage the most parallelism possible, we're using lots of boxes, which means that we aren't going to be able to necessarily use that same shared memory paradigm where we can just read and write to the same chunk of memory, because the chunk of memory that I'm writing to might be on a totally different box than the chunk of memory that the other processes are reading to. So we have to send messages. That's the big difference here, is we're now going to have to send messages from point A to point B, although there are many other ways to send messages that we'll see today as well. The network becomes extremely critical. And so we've already kind of talked about the network. We had that whole lecture about that a few weeks back. Communication is a huge part of performance. That's true with shared memory as well. But when you get into the message passing, it becomes a lot clearer. It's a lot more interface, right? Because you're actually seeing those calls in the code and actually can see that, oh, yeah, I have to wait at this point in time until this message comes in. with OpenMP especially, a lot of that stuff is kind of abstracted away from you, kind of hidden behind the curtain. So it's not something you necessarily have to worry about as much. Latency becomes a big enemy. So just the amount of time that it takes for a message to travel across the network, right? Is the definition of latency for all intents and purposes. There are other things that go into it too, I suppose, but the big one is just, if I send a message now, how long is it actually going to take? Travel across the wire and reach its destination, because that entire time, if the other process is waiting, they can't do much else until that time is elapsed. So those are kind of the things that we're fighting against. Data distribution becomes a lot more of a critical part, and that's our role as a programmer. That's arguably kind of the biggest thing that we have control over. We can't control the network. The network is what it is. We can't control the latency, right? It's going to take however much time it takes. We can control where the data is. So we can control in which memory banks the different chunks of data are put in. So it's kind of our job to think about this as we're writing our programs and do it in such a way that if they do need to communicate, they are as close to the data that needs to communicate with each other as close together as it possibly can be. So let's talk a little bit about the message passing interface. It is actually a language independent protocol. So it's not written, it's not meant to be in a particular language. That being said, I think C, C++ is by far the most common language that you're going to see used with this particular protocol. It's fairly old. I would argue surprisingly old, considering what we're talking about and what year it is now, and we're still using it, right? So way back in the early 90s was when it was first formulated. And the whole idea is that it's managing processes. So they call them ranks. We'll see that word rank used a lot today. When you see the word rank in MPI, think process, because that's exactly what it is. Keep in mind that processes and threads, like we've been doing in the past, are not the same thing. They are different, though they share kind of some similarities. But we can even use, threads and processes together and combined our programming paradigms, which we'll probably talk about a little bit later on today as well. The big thing that's important to understand about MPI, in my opinion, is the communicators, and sort of a subtopic within that is the groups. So a communicator, let me start at the end instead of the beginning. The processors or the processes that are running are broken up into groups, which are then encompassed by what are called communicators. And communicators you can think of as the admins behind the scenes that are overseeing that message passing process. The communicators are part of every single MPI process that gets executed. So if I run an MPI program that wants to have 8 processes, there will be some notion of a communicator on every single one of those processes so that they communicate with each other. It's like kind of the admin role. And the groups are kind of what the name implies, just logical groupings of the processes. In general, it is very easy to think of communicators and groups as overlapping completely, but that doesn't always have to be the case. It is also kind of easy to get in the habit of just using one communicator. In fact, I think all of the examples that we see in this class are just going to use one communicator. And that communicator is the communicator that contains all of the processes. It's called MPI COM world. So, and for a lot of cases, for a lot of programs, that's actually sufficient. It exists for a reason, and it's very convenient. It's very easy to use. But for more complex programs, there are certainly needs to break our processes down into smaller groups, smaller subsets of each other that are communicating for totally different reasons, right? As opposed to sort of the free-for-all that is implied when you use MPI COM worlds to have all of the processes communicate with one another across the entire program. We're not going to actually see a lot of coding examples of this But if you get more and more into it, if you actually are working on these supercomputers, it becomes a very important group and a very important concept. And then one other thing I think that's important to understand is the difference between communicators and groups. This is something that kind of stumped me for a while because they feel very similar, right? But a group is really just a logical grouping. If you look at the MPI API, which is sort of a tongue twister to say, you'll notice that groups allow you to do traditional set operations. So I can take the union of two groups, which would combine two sets of processes together into a symbol. Or I can take the intersection of two groups, which would find the processes that are in common between two sets, and then make a new set that just contains those common processes. So groups are made to help programmers specify exactly which processes should be together, right, based on whatever problem it is that we're trying to solve. The communicators then take in a group and facilitate the communication between all of those processes. And that's the whole. If you're using MPI-COM World, though, you probably won't be messing with the groups too much at all. We won't be messing with the groups too much at all. It does get very complicated very quickly, but I think that's an important feature within MPI, one that is important to know, especially if you are ever going further down the rabbit hole of trying to do these kinds of massively parallel programs. The other important parts of MPI, so point-to-point communication is kind of the basics, kind of the basic building block. I think we've already seen little tiny hints of this throughout the summer. We're going to see a lot of it today. This is the primary form of communication I think we're going to see on the fourth homework assignment. It's kind of exactly what you think. Point-to-point meaning I'm process number 2 and I need to send a message to process number 7. So it just sends that message directly across. There's a lot more that goes into it, as we'll see as we start looking at some more specific coding examples. But this is a very general purpose kind of communication that is useful for all kinds of things. So we can use it for very patterned communication or more irregular communication. We'll see a similar kind of technique that we saw with OpenMP, where we'll designate one process the sort of the master process or the one that's in charge, and then it oversees communication across all of the other processes. And the interesting thing about this is that we'll take a look at when we get to some coding examples. We've got both blocking and non-blocking versions of message passing, message sending available. That non-blocking were very useful for when I want to send a message, go do something else while that message does whatever it needs to, and then come back later and see if I have anything waiting for me in return. So the other part, which I think this is kind of a repeat slide that we've seen in past classes, are all these collective operations. So MPI allows various forms of communication. We'll see at least a couple of these in our examples today. Broadcast meaning, well, you can tell from the diagram, right? Taking a chunk of data and shipping it to all of the other processes, or scatter being to break something up into chunks. That's a very useful one, especially when you think in the context of like an array. So I can use a scatter operation to section an array up into chunks and spread it out. Gather being the exact opposite of a scatter operation. And reductions we saw with OpenMP, kind of the same idea with MPI, where we take values from all of the processes that we're communicating with and consolidate those values either by using a sum or multiplication or averaging. Some arithmetic operation gets applied to a piece of data across all of those processes. With MPI, one of the things that's important to keep in mind whenever you're sending messages is that the data type is important. But when you call the functions, when you call the message passing functions, right, you can't just plug in a variable and have it automatically figure out, okay, I'm sending a float. That means that I need to have this much data, waiting in a buffer on the other side to receive that float. We actually need to give it some help. And this is clunky, but also a good thing, especially when you consider that this is such an old protocol. The data types have changed, have evolved over time. So allowing the data type to be kind of abstracted away from the data that we're sending gives us more flexibility in terms of the size of the data that's being sent. So, if you're sending an int, you have to tell it, hey, we're sending an int. Typically that's 4 bytes, but not always. So again, these details kind of let us not worry about that so much and let MPI figure it out. But then in practice too, we also sometimes want more complex data types than just standards. So if I'm sending a structure of data, for example, we can use contiguous types, which allow us to essentially glue a bunch of data types together and then send messages that say, hey, we're not just sending one data value, we're sending this big chunk of data that comes in this particular format. I believe we have an coding example of that a bit later on as well. So here's how the actual message passing works in detail. The sender, of course, has to specify a valid destination and the receiver has to specify a valid source. These seem trivial, but can be easy to get wrong, especially if you're running programs that are going to be changing the number of processes. Like if I run one process, if I run one program with 8 processes, and then I run that same program with 16 processes, that's going to change the communication pattern that exists. So a lot of times we're using arithmetic or some other operation to determine the sender and the receiver. And if you get that wrong, you could end up trying to send a message to a process that doesn't exist, or trying to receive a message from a process that doesn't exist. So while it seems pretty trivial, a lot of times I'm not just hard coding in a process number there. There's math involved with it. The communicator has to be the same. So I think that's also one that seems pretty obvious, but can be a little bit tricky if you're using lots of different subsets of processes. Fortunately for us, we're not going to be. We're going to be using the world communicator for everything. So that's not one that we have to worry about in particular, but certainly is a concern for more complex programs. There's something called a tag, which is exactly kind of what it sounds like. If I'm sending lots of messages, I can use tags in whatever way I feel like. Maybe I want to prioritize messages, so the tag will represent, lower numbers are higher priority than smaller numbers are. Or maybe I just have 2 kinds of messages, and in certain parts of the program I need this kind of message, and in other parts of the program I need the second kind of message. We can use tags to help us distinguish that. In our examples, since they are kind of smaller, on the smaller side, our tags are probably just going to be the same all the time. We're not going to distinguish between different types of messages, but that is a nice feature that is available. And then this last one is certainly something that we do need to care about. On the receiving side, they have to have a buffer, which essentially just means they have to have a variable declared, right? They have to have memory allocated for the message that is coming in. And if it's not large enough, then the communicator is going to see that and say, hey, you tried to send me 8 bytes of data, but there's only 4 bytes here. On the receiver side, I can't cram 8 bytes of data into a 4-byte slot. That's not going to work. So all of these things have to happen, and all of those are on us. Every single one of those points is on us as the programmer to ensure are correct for our program to execute successfully. Let's talk about a comparison real quick between MPF, which is what we're talking about today, and OpenMP, which we've already talked about in the past. I think the first one is kind of obvious. I mentioned that right up at the top. Right? MPI is for distributed systems, and OpenMP is for shared memory systems, and the execution unit reflects that. We're using processes, threads. OpenMP is, I think, a lot more programmer friendly. We haven't actually looked at any coding examples yet, but we're about to, and I think you'll pretty quickly see that. Oh, hey, this is a little bit more complex. This is a little bit more effort, a little bit more work than OpenMP, which I can just take an existing program and just put pragmas on my for loops, right? And that's going to get me some parallelism. MPI does not work that way. In fact, I have a couple of examples that show here is a serial version of the program, no processes, no threads. And here's that same program parallelized. And so we can look at them side by side and see like, oh, wow, we actually had to do all this extra work just to get the parallelism up and running. We have a couple of examples like that that we'll look at pretty shortly here in just a little bit. And then this last one, perhaps more importantly, the network becomes a much bigger factor of communication. With OpenMP, we don't have to worry about the network at all. We don't use the network one bit. So it depends more on the architecture, depends more on how much memory we have, how big the cache is. Actually, those things, of course, still affect MPI as well. We're not immune to making trips to memory and cache effects, things like that. But in general, latency across the network is worse than all of those things in terms of the amount of time that it takes. So that ends up being the bigger bottleneck there, which is why part of the reason why we spent all that time talking about various networking configurations a little while back. At this point in time, okay, yeah, we're getting there. So here are some little tips, some of which I think I've already mentioned. But if you're writing MPI programs, each process is given an ID, much like each thread is given an ID in OpenMP. And you can ask, there's an API call. So this is actually another kind of similarity between the two. You make an API call to say, hey, which process am I? And then this is also kind of like what we were doing in OpenMP. We specify a master process or a main process. Usually process number 0 gets that designation. And we use it to do any work that has to happen once. Or if there's any coordination that has to occur, process number 0 is the designated one that's going to get that up, do all that organization. MPI COM World, I already mentioned, is the kind of default communicator. We'll see that in use here in just a moment. And this was true actually with OpenMP as well as MPI. How we break up the work depends on how many processes we have. Array, for example, with n units, then I'm going to probably divide n by the number of processes to try and break it up as evenly as possible. But that's true of OpenMP as well. We would use that same technique there too. So nothing too new in that regard. All right. At this point in time, it's time to take a look at some actual coding examples. For these coding examples, I'm actually going to run them slightly differently than how I will show you how to run the homework assignments, which I'll talk about probably after the break when we get more towards the homework assignment part of things. But I would encourage you to follow along with me and get some practice doing this, because this is what you're going to be doing on the 4th homework assignment, even though we're not quite running the actual assignment code just yet. I'm going to go ahead and fire up a Linux lab machine. And there are a bunch of examples on Canvas, which I'm going to load up here in just a second. And we'll start taking a look at them. Some of them you will actually recognize, I think, from prior conversations that we have had. You can also do these things through Shell too. I just have a little bit of an easier time navigating through the windowed version of the Linux lab. Although when we get to the homework assignment, it's actually maybe even slightly easier to do it on Shell, I would argue. Though you can do it through here as well. So I'm going to start by going to the calendar page for today and downloading all the MPI examples are in this MPI zip, which I'll go ahead and download and then extract. Oh, I still have them up from before. Well, I'll make a fresh copy. That's fine. Just doing some testing and debugging before class just to make sure everything still functioned properly, and it does. I had to make a few tweaks, but mostly still works. That's right. Okay, So this stuff is in my downloads folder in the MPI directory. Here we go. Here are all of my MPI code examples. We're going to start off with the really simple ones and then kind of work our way up to some of the more complicated ones. But before we can do anything, we actually have to take a moment to talk about how to compile and run these programs. If you try and compile and run them using the standard, G++ compiler, it's not going to work. We have to use the MPI compiler to make these things work. But the MPI compiler, which is MPI C++, is not loaded on these machines by default. So we have to load up the module first, which for our purposes is going to be the tau MPI module. As it kind of implies there, this also will allow you to use the tau profiler on these codes if you would like to. It's not going to be a strict requirement on the fourth homework assignment for you to use tau, but the option is there for you to use tau to profile these codes if you would like to. Once we go ahead and get that module loaded, now we should hopefully have access to the MPI C++ compiler, and it works just like the traditional compilers do. So we're going to start with this simple hello program. So we can compile it using the traditional means. Whoops, that's not the file name. This is the file name. There we go. Something like this should do the trick. Okay, but that's only one half of the equation. The other thing to keep in mind about MPI is that we can't run the programs traditional way either. We have to use MPI to run these codes as well. And so there are two ways to do this, and one of them is called MPI exec, and one of them is called MPI run. I think they're exactly the same. I'm not quite sure why they have two names for it, but I'm pretty sure, as far as I know, they do exactly the same thing. So it doesn't really matter which one you use. But you'll go ahead and say MPI run followed by what you would like to execute. And oh, that's fun. I'm not sure what this is about. I don't think that really matters too much for us, but it is a little concerning. I'm going to ignore it for now until I can determine that it actually is a problem. But anyhow, this is a simple hello world program, and you'll notice that it just prints out message from task number 0. Wait a second. This was an MPI program. I thought there were supposed to be multiple processes running, right? Well, there certainly can be, but if we want there to be multiple processes running, then we need to use a command line argument for that. And in a lot of cases, not all cases, there are some exceptions that we'll see a little bit later on. But with the -n flag, I can say, okay, I actually want you to run this with 4 processes, not just one. So it defaulted to 1. But okay, now I can run it with 4. Let's take a look at the code though, because this is going to use some of the very basic but also commonly used MPI API calls. So first off, you'll notice that we do have an include here for MPI. That shouldn't be too terribly surprising. By the way, I should mention, all of these examples, if you want to refer to them later / get a little bit more info than I'll probably have time to cover. All of these examples come directly from the MPI tutorial posted by Lawrence Livermore, National Laboratory. So there's a whole lot of other information and exercises that I'm not going to do if you want to get a little bit more practice and take a look at some more MPI examples. You can take a look at that later. But back to this hello world example, we declare some variables, and then right off the bat, we just start with some MPI calls. So MPI init, we're going to see that one in every single program that we take a look at. It does pretty much what you would expect. Make sure that every process has a number assigned to it. Make sure that the world communicator is up and running, because that was provided to us by default for every program that we run. The next command, MPI com size, is asking how many processes are in this communicator, which because it's MPI COM world, it should be the total number. It should always be the total number. If it was a different communicator, which again we're not going to see, but could happen, then it certainly could be a different number. But for this case, this is basically asking the question, how many processes do we have? And then make sure to stash it into this variable. And then over here on the next line, MPI conf rank, there's that word rank that I said was going to be popping up a lot, is asking which process am I? So tell me which of all the processes that exist, which one am I? Give me my rank number and stash it in this particular variable. And then finally, this call here gets the host name, which in this example is not terribly exciting because we're running this all on the same box. Later on, I'll show you how we can run it across multiple machines. It takes a little bit more effort to get those kinds of jobs up and running. But when we look at the homework assignment, I'll talk about how we can run things across multiple. For now, though, not terribly exciting. As we saw in the output, all of the host names were the same because all of these processes are running on the exact same box. And then here's that programming, technique that we already kind of saw with OpenMP and talked about a little bit, where we have a master, usually up here defined as a constant, that if there's anything that needs to happen once, we'll just use the master thread. So the master thread prints out how many tasks there are. But the interesting thing about this, that's, I think, one of the trickier things to get used to, it's a little bit harder to visualize in this program because so much of what's here is just API calls. But this is going to get executed by every single process. It's true for all of the codes that we're looking at today. We're writing these codes, we have to remember that, every single process that I am firing up is going to execute the whole program, top to bottom. So if there are sections that I don't want every single process to execute, we have to fence it off. This, make sure that, this is only going to be done by the master process or this subset of processes, whatever the case may be. And then finally, this finalized call just wraps everything up, deconstructs all of the MPI objects and stuff so that we don't have fun little memory leaks and things like that. This one not too terribly exciting, but let's move on to our next example. I want to talk about blocking versus non-blocking sends. So we've got two examples here, one called hello bsend for blocking send, and one called hello nbsend for non-blocking send. Let's take a look at the blocking one first. So this is an example of it's very similar to the last program, but now we're actually sending point-to-point messages. So what we're doing is we're taking the total number of processes that we have, putting them in half. So if I have 8 processes on the first 0 to 3, send messages to the back from or to send. That's the idea. So it's an example of patterned communication and breaking our problem up to send these kinds of messages. But this is also our first example of seeing a point-to-point message being sent. So take a look. Here is our send message. You can see that we're sending, let's see. So this is where we're sending it. No, I'm sorry. That's not correct. I think this is the actual message that is being sent. I can't do this from memory. I need to look it up. Okay. This is what we're sending. Yeah. So the buffer is what we're sending, the number of elements that we have, the data type, the destination, the tag, and the communicator. Awesome. So we're sending our task ID. We're saying hello from task number 0, hello from task number 1. We're sending our task ID. We're just sending one of them. It is an int. This is where we're sending it to. This is the tag, which by tagging everything with the same value means that we're not really using the tags. We're just we still have to put something there, right? But we're not really using it. And this is the communicator, which again, you can see is always MPI COM world. um, so that we can communicate to any of the other processes that exist. If we were using other communicators here, then of course we could only communicate to the processes that belong to that communicator. So could end up trying to send a message to a process that we can't actually access, for example, but not going to have that problem here. And then we have the receive message right after. But pay attention to how this is laid out and why it's laid out this way. This first if statement is saying if my task ID is less than the total number of tasks over two, and then the second one is for the second batch, but pay attention to the fact, notice that it is reversed. The if I'm in the back half, I'm going to receive the message first and then send it. It has to be that way. It has to be that way. These are blocking calls, which means that once task number 0 gets here, it'll execute the send, and then it sits there until the send is done. And then it sits here until it has received the message. And then on the opposite side of things, if I'm task number 5 or 6 towards the end of the line, then I'm going to sit here and wait until I receive that message. So that message never gets sent if they're both sitting there waiting to receive a message. And we did deadlock, a situation where they're both going to be blocking, waiting for that receive call. I am actually going to try that out in just a second. And see what happens, but we'll run it the proper way first. There's a couple of other slightly interesting questions I think to think about here as well. But let's go ahead and run this the way that it's currently set up before we play around with it too much. Vsend. Okay. And then MPI exec or MPI run. Make sure to pass in a -n, and I've been using 8 as an example, so I'll use 8 processes here for this example as well. Great. So task 0 is partnered with task 4, and 4 is partnered with 0, right? That's kind of what we would expect. Hello from task 1, hello from task 2. They all get printed out. They all tell us who their partners are, and everything seems to be working out pretty well. I see hello messages from all of them, 0, 1, 2, 4. But what you'll notice is that if 0 is partnered with 4, I'm always going to see the 0 message before the 4 message, right? Uh, 1 is partnered with 5, so I'm always going to see the 5 message, or I'm sorry, the 1 message before the 5 message, never the other way around. Never, never, ever, ever the other way around. What happens if I run it with an odd number of processes? What do we think? Kind of an interesting one to think about, right? What's going to happen? Any ideas? Try it out. See in a second. There's going to be, well, it's integer, I believe it's integer division. So it would be one more sender than receiver, or one more receiver than sender. I'm a little unsure myself which one it actually would be. Welcome, welcome. No, you're fine. We're doing some MPI coding exercises. Try and catch up with us. Let's try it out and see. Okay, so we see that task 1 is partnered with task 5. No, that was the last run. Sorry. Task 0 is partnered with task 2. So we have one more receiver than we have senders, actually. That's finally telling me. 2 is partnered with 0. 1 is partnered with 3. 3 is partnered with 1. Who's partnered with task number 4? Nobody. We've got an extra receiver task that is not partnered with anyone at all. We're stuck. We're stuck right now. So task number 4 is saying, hey, I'm expecting a message from who's task 4 even expecting a message from? I'm not quite sure. I have to look at the code real quick to see. Task number 4 is going to be, well, from process 2, it thinks it's partnered with process 2. But process 2 thinks that it's partnered with process 0. right? Or process, I don't remember. It actually said, yeah, from 0. So process 2 was already spoken for, and actually process 2 isn't even in the process, it's in the receiver's half, trying to receive first before it sends. So we hit a deadlock there, and I had to control C out of it because that person was sitting there waiting for a message to come that was never going to come. It's never going to get there. Um, so our first example of, hey, you really have to be careful with this stuff. Imagine, well, it would never get this far, but if I was running this program on a big old computer, using up all those resources and this happened, that would be a huge waste of time, energy, money. Of course, we're going to test this locally first on smaller scale before we scale it up to that big scale. So hopefully we would never get to that point, but these are the kinds of problems, these are the kinds of issues that you're going to run into when trying to program using MPI. The other thing that I think is somewhat interesting to think about is like if we were to simply reverse these calls, how do I paste this in again? What is the vim command for that? I don't actually remember. Suppose I could just copy it from the first if statement, even though it's slower. Oh, I guess I forgot to mention this additional status variable over here when receiving, but it's pretty self-explanatory what that is. Any error codes or other things will uh, be caught by that. We do have to recompile this since I changed the code, and then we can rerun this with, even if we rerun it with an appropriate number, an even number of processes, right? Oh, well, it proved me wrong. Wait a second. Oh, I think I know why that is. Yeah, I think I know what happened there. The order does matter, but I happened to pick the order. It doesn't matter. If they were both trying to receive first, that would be a problem. But because they both were sending first, that actually is not the problem. So I would have had to do it the other way. Would have had to flip flop the ones at the top. My bad. I picked the wrong ones to flip flop. The sending call being blocking is really not that much of an issue as the receiving call being blocking. For the sending call to be considered complete, all that it has to really do is make sure that the data has been put off onto the wire. The communicator just has to be like check over all the stuff and be like, yep, everything looks good, right? So uh, that's not really the blocking that's the problem. It's the receiving part that's the problem. So I would have to I'm not going to flip flop them again. That I don't need to take the time to do that. But if we did do it that way, we would start to see that nothing's going to get through. Everything is just going to come to the screeching halt right away because everybody's waiting for a message that hasn't actually been sent yet. So those blocking calls are ones to pay attention to, but we can also talk about the non-blocking version briefly here. Starts out very similar to the blocking version, but you'll notice that the if statement is a lot shorter here. So the if statement is just computing our partner this time. And then here's the non-blocking receives and sends. And oh, you can see actually the receive is first. It really doesn't matter in this particular case because even though the receive is happening first, it's not blocking. So something else, you can go off and do something else while you're waiting for that call to finish resolving. Um, the additional piece of information you need with the non-blocking call, you'll notice there's an extra argument out here for the non-blocking call. So you do have to have these request objects. Think of them similar to like a promise, right? In other languages that you can refer back to see that, oh, hey, this is actually finally completed now, and I can finish the message passing process. Um, and then you'll notice that after the receive and the send calls are made, there is this call to wait all. which is doing exactly what it sounds like. It's making sure that everybody's reached that point before proceeding on. So it's a barrier, in other words. That's an example of a barrier to make sure that all processes have reached that point before finally going through and continuing on with the code. Let me compile and run this one real quick. It should be as easy as changing this compile string a little bit. And then running it. So now we can see that even though task 2 is partnered with 6 and vice versa, I think it's not quite as guaranteed, although I don't see any that do flip-flop here. Looks like there's still, probably just because of the order, the earlier processes are going to be spun up first. So they're probably still fast enough. But I don't think there's any reason why they would have to appear in that order like we saw um, on the first program. Still not seeing, well, task 7 is here we go. Task 7 is partnered with task 3, and we see that 7 actually made it before 3 did because we used non-blocking calls. That would not have been able to happen in the previous example that used the blocking sends and receives. Is that a good thing, a bad thing? Both, neither. It depends on what you're trying to do, right? Depends on the problem you're trying to solve. One thing that I think is still true is if we make this 9, we still end up with an on process out that is waiting for a partner that doesn't know that it's a partner with that particular process. So we still have that problem here, but we don't have some of the other issues with this particular program. Cool. All right. Next, let's take a look at an example of a collective operation. So a collective operation is one call that sends out multiple messages. So all of the examples we've seen so far is, one call to MPI is just going to send a single message from point A to point B, point-to-point communications. Collectives involve sending lots of messages, multiple messages per MPI call. So if we take a look at the MPI scatter program next, this is almost exactly the same little example that I was talking about earlier on today, where we have an array and we're going to take that array and chunk it up and distribute it across multiple processes. So here's my very small 2D array, 4 by 4. We go ahead and initialize MPI, get the rank and the size, and then here's our scatter operation where we're going to, let me back up a second. This is what we're sending. So we're taking this entire array and we're sending it out. The send count is based on the size, which here is defined as 4. That's maybe not the best name for that constant, but it's intended, I think, to be the size of the, or no, that's that's the size of the chunk that we're sending. 4 values. They're floats, so we're sending 4 floats. This is the name of the buffer that we're going to receive those floats in, which is declared. Should be declared somewhere. Oh, here it is, right here. Boop. And then how much data we expect to receive on each end, also floats. The source is the process number that is doing the sending, which is defined as the first, well, process 1. I guess it doesn't really matter, right? But regardless, once we get through that scatter call, which is blocking, so even though this is written once, it affects all of the processes that are. So there is no fencing here. There is no, if process equals 0. The fact that this exists defines the source right there in the call, is process 1 being the one who sends out all of that information. It is going to affect every single process such that once this call is done, all of our processes will hit this print statement and print out the chunk that they received. Now, the way that this is written is perhaps not the best because you may have already kind of deduced slash seen from the message down here that there this is written in such a way that it has to use four processes. Otherwise, it doesn't work. I'm taking this 4 by 4 two-dimensional array, splitting it into four chunks, sending it out. It will not work with any other configuration, which is why they go out of their way to not even try it if you do anything other than four processes. In a real world example, you would probably want to make that more flexible. You probably want to adjust it to your array would probably be bigger as well, right, than 4 by 4 for the kinds of problems that we're talking about. Um, but just to, for completeness sake, run this one before we move on to our next examples. So if we run it with anything other than uh, dash n of 4, it's going to fail. And so you can see that rank 0 got the first row, and so on and so forth. So with one call, we sent, in this case, 4 messages. They all originated, I believe, from rank number 1, but then got sent to all of the other processes. Although I would hope that it's smart enough not to actually send a message from process 1 to itself. Was that your question, or do you have a different? You mean just like take an element out of the array? Well, let's try it out and see. I'm always open to experimentation. Actually, I don't can C even do jagged arrays is my question, I guess. I know like Java, I can have non-rectangular arrays. I'm not sure that C will let me make an array that isn't rectangular. We can certainly try it and see. Kind of expecting. Well, it compiled. Yeah, I I learned something new today. I didn't know C could do jagged arrays. Apparently, it does not care. So cool. Awesome. Oh, you think if it was in the middle, it might be a little different? Let's try it. Let's try it. Take that guy out. Oh, we still need that comma though. Still compiles. And so it added an extra 0 on the end of that row. Yeah. Which, I mean, is still, and there are worse things that could happen, right? Like it could have crashed. It could have not compiled. It could have failed in some other way. I guess you don't necessarily always know what's going to be in that memory spot because we still allocated a 4 by 4 array. So it did allocate that whole chunk of memory. Does it zero it out when it does that? I'm not so sure. I'm sorry? Oh, yeah. No, it didn't fail. It just charged ahead. I would have expected a warning at the very least, like, "Hey, you told me this was 4 by 4, and I don't see 4 by 4 things in it." I was expecting the compiler to complain a lot, and it didn't complain at all. So that's interesting to me. But I don't think that's MPI's fault so much as it is C++'s fault. Yeah, I don't think that has anything to do with MPI. Um, all right. I wanted to show you an example of making a more complex data type. You actually won't need this. Actually, I can't remember if the homework assignment uses this particular technique or not. I kind of think that it doesn't, but we'll take a look at it. Um, so if I want to send something that's not just a single value, right? That's not just a single int or something like that. How do we do that? A little bit of a contrived example because I'm really just kind of doing the same thing that I was doing before, sending a single row of data. This is actually functionally the exact same example, right? We were doing before, but not using a scatter operation, using point-to-point communications instead, using sends and receives. So hopefully also an example of like, hey, these collective operations are really convenient and you should use them because it will help make your life simpler if you do. But this is doing exactly the same thing, taking this 4 by 4 array, chunking it up into 4 different rows, and then sending them out. But look at what it has to do in order to make that happen. Uh, this is the kind of newish stuff here, or the beginning of the newish stuff. We have to define a new contiguous type. So I'm saying, hey, I want to define a new type. This many floats. In this case, size is 4. So I'm defining a new type that is not just one float, but is 4 floats packaged together. It doesn't have to be necessarily all the same types of things. There are ways to package things together as like structs and so on and so forth. So it's a very simple example. The way that you would kind of do this, the way you maybe kind of think about this is once you commit this as a new contiguous type, I can then use this contiguous type to define other contiguous types, kind of build things up together that way. So, but this is just a very simple example, as I said, that defines a contiguous type as not just one float, but 4 floats all packaged together. And then down here, instead of using the scatter operation, you can see we've got a loop that's going to have to send out each one of these rows one at a time. So we're sending out first row, second row, third row, so on and so forth, and then receiving all of that. We're using blocking calls in this case. All the sends go first, and then all the receives happen after that, and then we print out the values. This one, I'm not sure I really need to run and show you. It's going to look exactly the same as the last one. Really just more an example of, well, so 2 things. Using those contiguous types, we have to define them and then commit them, which is essentially making sure that they are part of the MPI collective consciousness, as it were. And then the additional overhead that's required to do things that way. Use the scatter operations. It's certainly going to save you some time. The last examples that I have to show you are examples of here's how I would do something additional. Here's how we do that same thing, parallelize on MPI, just to kind of compare and contrast. So the first one has to do with an array, a bunch of array operations. I want to take a look at the serial version first. So there's actually no MPI in this next example. It's a serial program that just does some very basic arithmetic with arrays. You can see that the array is initialized to just some very simple values. What is the array size set to? Oh, it's gigantic array. But it does some very simple, array arithmetic, some multiplication, some addition, and then it doesn't print out the whole array. It just prints out some of the chunks of the array. But just for completeness sake, since we are going to compare it against the MPI version here in just a second, I'm going to go ahead and compile it. We don't need to use the MPI compiler here, right? We can just use the traditional G++ compiler, since there's no MPI in that at all. And then if we run it, oh, we get a seg fault. I was worried about that actually because that constant at the top, we ran into this problem. Was it when we were doing OpenMPI? If you make arrays too big, it gets unhappy, and I feel like this is too big. So we have to take at least a 0 or 2 off of there, but that's gonna affect these down here as well. So we have to get rid of this line because this doesn't exist anymore. All right, sorry about that. I missed that bug. There we go. Okay. Maybe I didn't have to take off 2 zeros. Maybe I could have gotten away with taking off 1 0. I don't know. But, it does some math, prints out some of the results. But let's take a look at if we wanted to parallelize this. So first off, where is the parallelism in this code? Where's the stuff that we can do in parallel? I'm always going to take a look at the loops. Maybe not the initialization loop, but this one here, do some simple value assignment to each of the array elements. So, okay, it would be nice if I could take this array, like in the previous examples, chunk it up into different chunks and then have each process do a certain chunk of that array. But what does that look like? How do we actually write the MPI code to make that happen? What's the difference between this program, which seems kind of simple and straightforward, versus the MPI version? So there's an MPI version called, oh my gosh, MPI array. Probably don't need to compile and run this one because it looks exactly the same, essentially as functionally exactly the same as the one that we just looked at. Although the array size is even bigger on this one. That's fun. They even cranked it up a little bit, but that's okay. Uh, Once we get past all of the initialization stuff, that's not really the bad side, the bad stuff. Here you'll notice this is starting to look kind of like the GPU code almost, where we've got chunk size and leftovers. So what happens if the number of processes that I have doesn't evenly divide into the array? We have to take that into account. So that's extra arithmetic involved. It looks like we've actually got some tags involved this time. So to track different types of messages. And then right away, we're saying that the master task is going to go ahead and do all of the initialization. That makes sense, right? To have the master just do all the initialization. That's not the parallel part. But then the master task is also going to do all of the sending. So break up the array, send the portion of the array to each of the other processes so that they can do their particular data. And you can see that it's actually sending two values here. It's sending the offset, which is where you begin, right? This is the index of where you begin in the array, and also the chunk of data itself, because it's not going to have access to all of the array. Um, it's only going to have access to its particular chunk. We're in distributed memory here, right? So it needs to know both values, because the actual arithmetic that's being performed, which is all the way down here, you can see how much more code there is, depends upon the index. So we have to pass the beginning index as well as all of the data in the array itself. So that's two separate messages. And it uses two sends to do that. One for the initial index, and then one for all of the actual data itself. So you can see that it's sending all of this data, right, to all the different ones. And then the master process also is doing its part of its work by calling this update function, which is what we're just looking at down here. This is the actual arithmetic part. This is the part that's pretty much copy pasted from the previous one. But if going back up to here, then once all of that work has been done, we have to get the data back in one place. So the designated master process is now receiving, right? Receiving messages that contain all of the data, and actually then finally using a reduction to compute and print out some of the sample results. So lots and lots and lots more work happening here. Every single one of these is based off of, again, using arithmetic to compute, and unlike some of the examples we saw before, doing so in such a way that it will work with any number of processes. So the example that we saw before is restricting us to 4 processes, which is very inconvenient. This is written in such a way to work with any number of processes so that we can scale it up as much as we would like to. But notice, again, just notice how much more work there is involved here, right? How much more work there is to actually, oh, we didn't even get to the non-master stuff down here, although not terribly surprising. Receive the data that you're getting, receive my index, receive my part of the array, do my work, and then send the results back. Um, so, uh, lots of additional overhead, lots of additional thought that has to go into these programs. For we kind of talked about this when we talked about speed up as well, right? Because there's additional serial work involved here too, additional work that is happening just to set up the parallelization. It takes additional overhead, things like that. Don't underestimate how much of that work needs to be done. This is what seems to be a very simple example from a serial perspective, but as soon as you add MPI in the mix, as soon as you try to parallelize it, it becomes a lot more complicated. Fortunately, this is sort of a well-solved kind of a problem. Lots of people have studied these kinds of things, and you can probably piggyback off of this example if you ever find yourself doing this kind of situation. Let me show you one more, and then we'll take our break. I want to show you this one because it's one of my all-time favorite problems, and also one that we've talked about already. It's a Monte Carlo. This is actually a Monte Carlo problem. Not the heated plate one that I know some of you are working on right now, but the one about computing pi off of throwing darts. So figuring out which of the darts land within the circle and then using that to compare, using that as an approximation for the area of the circle and then using that value to compute darts. Here's an example of the serial version. So no MPI, no parallelism involved at all. It is a pretty darn simple for loop. Although they do have an additional function down here. I would have probably left the function out, perhaps, but whatever. They also, I think, kind of overcomplicated this. Well, they didn't overcomplicate it. The way that it's written is in such a way that you see the value of pi updating over the execution of the program. So they throw 10,000 darts. Pi is this number, and then they throw 10,000 more darts. Say, all right, 20,000. Pi is this number. So you can actually see the progression. Maybe I should just compile it and run it for you because that part's actually kind of cool to see. Uh, no MPI involved, so we can just use. Oh, except I forgot my -o flag. So you can see that after 10,000 throws, we get 3.15, which is already pretty good, right? But as we throw more and more darts, you start to see it converge more and more towards the actual value of pi. So 3.14 is good, but then the next values are 159. So the one is kind of getting in there, but you still see it hasn't quite. Actually, even by the end of the program, it seems like, okay, here is where that next digit's finally locked in. It doesn't actually change after that. So it takes 80, oh, that's 840,000 throws just to get the first four digits of pi locked in. And they're not even going to 141. The next one is a 5. So this column should eventually converge to be 5. Not quite there yet, even by the end of this execution with 1,000,000 throws, which doesn't really surprise me. You have to throw a lot of darts to get it to actually work. You have to a lot of random throws to get it to converge to actually be super close to pi. But still, let's take a look at. There's actually two examples of this written with MPI, which are kind of the same story. Um, you know, just kind of looking and appreciating how much effort, how much work goes into taking what seems like a fairly simple problem and trying to parallelize it using MPI. So, of course, we have all of our calls. These are pretty standard, right? You're pretty much always going to do those initialization calls. But then we're sending out values saying, okay, you're responsible for, so every dart throw is independent. So I can just break it up. If I have 10,000 dart throws, I can have every process do, well, if I have 10 of them, I can have every process do 1,000 and then report back, right? And so that's what it's essentially doing here, dividing up those throws and then getting the results back from all of the workers. So each one of the workers is calling this dartboard, which is doing the randomness. Here's the random part of things right here, and keeping track of their own value of pi. And then the main process gets all of those values of pi back and kind of averages them together to get the actual value. Yeah, just the amount of overhead, the amount of work that's involved. Although there's a second version that I think is a little bit cleaner that uses a reduction operation instead of point-to-point values. So this is actually a second MPI version of the same program. You can see there's a single call to MPI reduce there that allows the code to be cleaned up significantly. I don't see any sends or receives anywhere. It's all just that one reduction call that gets everything done because all the processes are going to go ahead and compute their own version of pi. They use a reduction to collect all of those into the single main process and perform any final computations. Instead of sending point-to-point messages between all of the processes and the main process. So use those collective functions when you can is kind of the main story there. But as well, the other main story being like, hey, this is work. Parallelization is work. Getting MPI to work is not always simple and straightforward, especially even compared to like OpenMP, where I can just drop some fragments in and poof, my for loop is magically parallelized, right? Not the case for our MPI. Very different kind of feel. Um, Takes a lot more thought. It's kind of closer to the GPU programming examples that we saw than the OpenMP examples, in my opinion. I think those are all the code examples that I have for you, except for, of course, the final MPI code example we're going to look at today is the fourth homework assignment. But we're going to do that. We have a little bit more. I want to introduce that problem a little bit first before we take a look at that code. Does anybody have any questions about what we've covered so far? If not, we'll go ahead and take our break. We'll say 6:55. So we'll come back. We're going to talk about the in-body problem when we get back, because that is the problem that we're going to be working on with homework 4. And we'll take a look at the code for homework 4. And then it runs a little bit differently. So I'm going to talk about that as well. But yeah, hit the bathroom, grab a drink, and we'll start up again at 6:55. It's 75 seconds. Yeah, I won't say. It's it's fun. Oh, yeah, it's really strange. Oh yeah, it's not so it's just fun. That was a lost interest in my success. Yeah, the time and so yeah. So how many iterations are you operating before check? Should oh, oh no. Like yeah, so they said that all the numbers for the cell kind of yes. So like two what diagram. It's somewhere between 10. So it's significantly like sure it's oh really epsilon is equal to the difference between like the overall like total average right now and the total average before you be calculating it using just this batch uh, and divided by the total number of iterations that this
and the like average is uh is an average of absolutely everything. So it usually like sure makes sense. Averages is cool. It's the thing. But the first place is the thing was sorry. What the heck? What am I doing? Besides the trick yes. I mean, yeah, like I said, it's a 75 seconds. Which it was like 100 when I had like a much lower. See, I sort of see. Very good as a servant is I think maybe this you're going to that's an absolute yes, probably twice as good. That's thanks. Well, it also depends on this so I did not see results when there's two matches that I would watch. So that I'm just like every fucking season are the same thing. They're only purple is that I hate Florida. He did school last I gave you said that. Yeah, but I mean, it's like, but also, like, yeah, you didn't like, there are the ones that you're batch size with. One is 85 and the other one is yeah, yeah. It was all surprising, fine, not able, and then all that, doesn't so, not much time, hard as you take. Going, like, but you like it was so matter of yeah, I know you should only have one where so you take it roughly 70 or 70 good learning never so oh this like ending hold on a lot of shit. Um, yeah, it's not as good. Yeah, like all different things like yeah, in the lab, it's kind of a problem.
A quick question. Yeah, so for the question on the homework about the performance versus like plate size, what would you like to see for that? Because I have a graph for the like wall clock time and the like iterations to converge. I was going to talk about that. Was there anything else you wanted to see from that?
No, I mean, I think time is probably as good as any, right? That's usually what we care about is how long things take.
Right.
So if you've got a good graph showing time, I want to see, like big O of whatever, right? So, there's, I know maybe it's been a little while since you've,
Yeah,
thought
I was
about.
going to ask about that. So how remind me how to figure out how that works.
Well, there's a few different ways. I mean, honest, you can use the data. You can look at the plot and say, hey, if it looks like a parabola, then it's probably n squared. And if it looks like a straight line, then it's linear, right? So sometimes you can just visually inspect. Sometimes you can do it based on the code. So if it's nested for loops, each one going n times, that's classic n squared, right? So some combination of the two is usually what's expected. For the for the plate size, it's clearly going to be expanding. Is it square or it is rectangular? So it's not n by n. It's like n by m or something. I can't remember off the top of my head, but um, I would expect it to increase at least n squared, just because.
Right, that's what I was intuitively off the dome, but like just off the plot, I was like, is this n squared, or could you say it's like log? but I guess
Well, if it's like exponential or something, I think you would know. It would go up like almost vertical
I guess it
afterwards.
depends how what size you go to.
Right. And just look at the data itself. If you double, if it's n squared, that means that if I double the size of the plate, then I would expect the um, time to quadruple,
Mm,
right? So
right.
it would have that
Just kind of
relationship.
intuitive
Yeah,
stuff. Okay.
yeah, exactly.
And so I increased the size like squarely. Would you like to see like one dimension versus the other?
No, no, no. The way you did is perfect.
Okay.
Yeah, perfect.
And I think my numbers were like total points, grid points versus time, stuff like that. So,
No, that sounds great.
okay. Cool. I just want to make sure if there's something else you wanted to see out of this.
That's it. Sounds like you got it.
Cool. Perfect. Thank you.
I saw that. So I mean, we need to. Base. Like I see. Yeah, so I mean, this is a game. Yeah, that's so I mean, so she needs mom and oh, she said, oh, I spoke said, I spoke. No, gosh. That it's kind of disrespectful. I think they're there. I think they just play.
Yeah, I can imagine either.
Yeah, honestly, you just squandered your opportunity. You know, you got like 4 years. There's often been these kids, like.
Yeah, it's like I never even knew that all that involved. On this, like, in earth, you know, they do that.
Yeah, or this.
Yeah, did they get like more money? So,
I would hope, I would, I would hate, I would hate this.
we already lost. I don't know.
Yeah, I don't.
Yeah, then you go over it.
Oh.
Just like doubly lost this fence. Something. I stopped caring when Hallway lost. I took that.
Yeah.
Great.
I was just telling him how it's so upset during the screen. So Soros literally had like he could have went and done his own goal, but instead really he squandered 5 seconds. So there was like a controversy where it hit the line. Oh yeah. Someone guessed it was no interference, shift the ball, the carbon, and nothing happened. So clearly just like you saw it, right? Yeah. And you said nothing happened. Amazing.
All right, everybody. We got about an hour left to go, and we're gonna spend that whole time talking about the final homework assignment, which is based off of N-body problem. It's a very famous problem. People have been thinking about this problem for a very long time. You can see from the slide that it's formulated all the way back uh, in Isaac Newton's days. So not a new problem, but still one that we are working on to this day just because of how complex it is. When you think about how many bodies there are in the sky, how many stars, planets, other things there are out there in the universe, just absolutely massive amount of them, and also a massive amount of space that they're taking up as well. So a huge problem. This is kind of like the classical high performance computing problem, although and I don't know, there are some other ones that could argue for that claim as well, but certainly one that comes up a lot in conversation when you talk about supercomputers, high performance computing, and body problem is up there, no doubt about it. So let's talk about it. It is going to require us to talk about a little bit of physics. I promise that I'm going to try and keep it as simple as possible because this isn't a physics class. I recognize that not everybody's going to have a huge amount of physics background. We're going to try and keep it simple. I'm gonna try and keep it straightforward. We've got a set of n bodies in 3D space. That's of course where the name of the problem comes from. For each one of those n bodies, if we want to figure out where they're going to be in the future, we need to know / compute a few different values. We need to know where they are in three-dimensional space. So we need to know their x coordinate, y coordinate, z coordinate. We also need to figure out their velocity in all three of those dimensions as well. So what direction am I moving in the x coordinate space, y coordinate space, z coordinate space? Those values are based upon gravity. So based upon the other bodies that are around them, there's going to be that gravitational pull between those two bodies, pulling those planets or stars or whatever they are in various directions. So in the classical n-body problem, what we're doing is we are going to, for each one, let's keep the number small, just to keep it, able to wrap our minds around it, right? Let's start with the value of n being, I don't know, 100 or so. So if I'm looking at the very first one in that list, I'm going to figure out how far away I am from all 99 of the other ones. And then based on that, I can compute the effect of gravity on that is being felt by me from all 99 of the other bodies in the simulation. And so based on that effect of gravity, I can then compute, this is the velocity in the x direction, this is the velocity in the y direction, this is the velocity in the z direction. And the way that it typically works is it's going to be based on time steps, which we'll talk about a little bit later. But first, let's talk about, okay, this is very large. The problem I just described, what kind of computation time are we talking about? For each one of those bodies, I have to visit each of the other ones. So for n is 100, I have to then talk to all 99 other bodies, but then I have to do the same thing for the second planet, and for the third planet, and the fourth planet. So we're very quickly reaching n squared territory here, right? I have to visit each one of those for every single body, but very parallelizable because each of those bodies is independent of one another. So if I wanted to, I could say, here, you get the first 10, figure out the distance. Now, I need the data, right? I need to know where all of those other planets are. But as long as we have that, if we can distribute that data across all 10 processes, then I can have the first process figure out the motion for the first 10 bodies, the second process figure out the motion for the second 10, and so on and so forth. Very easily parallelizable. Problems that we have are with accuracy. So the time step comes into play. Time, of course, is continuous, right? It's just constantly happening, whether we like it or not. We're all getting older. We're all the oldest that we've ever been in our entire lives. But with the simulation, we have time steps. So everything is at this point in time, and then I'm going to move 10 seconds ahead into the future, try and see where they are. On a planetary scale, it might be bigger time steps than that, right? Because how far is the planet? Well, actually, they're moving pretty fast in a lot of cases. They might be moving pretty far in 10 seconds. But regardless, there is some time step, right? There's some length of time. I'm not analyzing it down to the nanoseconds. We can't do that. That's far too much of a resolution. So we just have to say, all right, I'm going to do the best I can to predict where I'm going to be 10 seconds from now. Move all of the planets, and then, okay, say, all right, where am I going to be 10 seconds from now? Move all the planets, and then say, all right, where am I going to be 10 seconds from now? There's a problem with doing things that way. It seems intuitive. It seems straightforward. It's simple, right? We actually have a name for that process. It's Euler's method. So we're saying that the position of the body we are currently at time t. The position of the body at t plus h, where h is however big our time step is, 10 seconds, 100 seconds, whatever. Sometime in the future, h is how far in the future we're looking, is based on the position where we are now, plus the time step in the future times the velocity. It's a classic physics equation. If you have taken any physics at all, you probably would have learned this at like high school level physics. Right? Motion of bodies, certainly entry-level college physics, right? So not terribly complicated to understand, but there's problems with this. Does anybody see what the problem is in terms of accuracy here? Think about the fact that, okay, I'm moving 100 meters in 10 seconds, right? 10 seconds from now, I think I'm going to be 100 meters over this way. Well, does that mean that 5 seconds from now, I was 50 meters away? And does that mean that I'm actually going to have the same velocity over that entire range of time? That's kind of what we're implying. We're implying the velocity is never going to change over that 10 seconds. That's not true because all of the bodies are moving continuously. So as soon as they move even a little bit, that velocity is changing, even if just by a little bit. And the more time that goes on, the more it's changing. So by the time we hit the end of that 10-second window or 100-second window or whatever h is, right? The actual velocity at that moment in time is actually very different from what it was based on the beginning of that window. As soon as that planet moves at all, its velocity is changing. It's constantly changing, just like time is continuously moving. The velocity is constantly changing. So this is a great simplification, but it's not accurate. It'll get us a good approximation, but the error compounds pretty significantly. The error for just a single time step is on the order of the length of time steps squared, meaning that for longer time steps, there's going to be more error with the motion, which you might say, okay, well, just make sure you use really small time steps then. That'll help keep the error level down. But then that means that if I want to compute, over the next year or 10 years, that I have to do a lot more computations with smaller time steps. So there's a big trade-off there, right? We would like to be able to do big time steps if we can, but we don't want to lose the accuracy. So there's a few other techniques. There's one called the midpoint method, where we actually try to estimate what the velocity is at the midpoint of the time step. So if our time step is 10 seconds, we're going to try and estimate what the velocity is at 5 seconds and use that to compute where we're going to be 10 seconds from now. The idea being that, okay, it should at least be, kind of in the middle. So the error from the beginning will maybe cancel out some of the error from the end. It doesn't quite work that way. It's still not 100% accurate. So there's even more methods. One of the more popular ones that you'll see mentioned in the literature is called Runge-Kutta. What it tries to do is it actually makes 4 estimations. One estimation at the beginning of the time step, one estimation at the end of the time step for what the velocity is going to be, and then 2 estimations at the midpoint. And then it averages all of those estimations together to be the velocity for that particular time step. This ends up being the most accurate method of the 3. But the point I'm trying to make here is that this is not as simple and straightforward of a problem as it might seem to be. Fortunately for us, and the code that we're looking at, all of these are already implemented for you, so we don't need to worry about all of the ins and outs. You're more than welcome to take a look. There's great Wikipedia pages about all of these if you're interested in looking at other implementations. Now, this actually is the implementation that we're going to be looking at. It's called the point-to-point method. So every body is compared against every other body, point-to-point. But that's not the only way to approach this problem. There are 2 other ways. We're actually going to spend a lot of time talking about that way. Barnes-Hut, that is maybe the most famous algorithm for solving an n-body problem. One of the most famous, certainly. But there are others as well. The particle mesh, I'd like to mention just briefly before we do a deeper dive into Barnes-Hut. The particle mesh implementation takes a different approach. What it does is it lays a grid, either 2-dimensional or 3-dimensional, depending on the problem you're trying to solve, over the entire space, and then it calculates what it calls potentials. So basically what it's doing is that it's going to look at every body and then figure out how much of a gravitational effect it will have at every single grid point. So if I am in the middle, we think about 2-dimensional space, just to keep things easier, right? If I'm a body, there will be 4 grid points around me. And so I'll say, okay, I would have this much of a gravitational effect on this grid point, this much of a gravitational effect on this one, so on and so forth. And we'll do that for all of the bodies on each of the grid points. And then to compute the velocities, we simply look at the potentials, the weighted potentials on all of the grid points that are closest to me. It can either be the 4 closest to me, or you can go another, the more rings out you go, the more accurate you're going to get. But the idea there is that, okay, I now no longer have to visit every single other planetary body in order to figure out the gravitational effects. I just have to compute my own gravitational effects on the grid points that are nearest to me, and then do the opposite to figure out how much of an effect those gravitational potentials are going to have on my own motion, which greatly reduces the number of force computations that have to be computed. So that is another way of thinking about it. But the one that I'd like to talk to you about is Barnes Hut. And what Barnes Hut does is it breaks the bodies up into regions. We're going to make a tree out of it. So this is a tree-based algorithm. If we're in two-dimensional space, it ends up being a quad tree. So we're just going to keep splitting the two-dimensional space into quadrants. And then we'll split the quadrants into further quadrants. And we just keep splitting until every single body is in its own individual quadrant, right? As you can imagine, if I have gaps, then some of the quadrants may not have to split down very far, right? So if there's a big gap with no empty space, then I'll just have one big, empty leaf on my tree. But then for more densely packed areas with lots of bodies, then I'll have to keep splitting until I get down to each individual one. We can, of course, do the same thing in the third dimension, but that makes it an octree. So there'll be 8 leaf nodes coming off of every node as opposed to 4 nodes. The way that it works, though, the way that we calculate forces and potentials in this particular case, first thing we're going to do is figure out how big my section is, because there are varying sizes, those quadrants. I actually have a plot here that kind of shows what I'm talking about, right? So you can see that as we get through to more dense pockets, these sections get smaller and smaller and smaller. But for the ones that are sparsely populated, we don't have to keep subdividing, right? There's nothing left to subdivide there, so we'll say that's okay. For each one of these, we're going to compute the actual physical size, and then also, essentially, we're computing the center of mass for this entire section. So that instead of having to worry about the gravitational forces of every single body, what we can do instead is use the center of mass for a particular section to represent a whole collection of bodies' gravitational force on an individual body. And because it's in a tree-like structure, what that means is that the root is going to be the whole thing. And then each one of the 4 quadrants of the whole entire big square is going to be the next level down. And then each of the ones after that will be the next level down, the next level down. So that means that we actually have an indication of the distance away the 2 bodies are based on how far apart they are on the tree. So if I have bodies that are down certain branches of the tree, that will tell me that they're farther away than bodies that are on the same branch of the tree that I am on, the body of interest is on. And we can use that to our advantage. What we're going to do is, for every node in the tree, we're going to compute the center of mass based on that section. So for the upper layers, right, inside of those nodes, even if they are broken down further, the smaller quadrants, what we'll do is we'll add up all the masses and compute the gravitational forces up for the center of mass of that entire section, which allows us to take shortcuts. Instead of computing the forces for one body against all of the other bodies, what Barnes Hut says to do, it says, well, okay, if the 2 bodies are close together, then we will do it for every single one, because those are going to have the biggest effects. But for bodies that are beyond a certain threshold, and that threshold is variable depending on the parameters of the simulation you're trying to conduct, right? For bodies that are farther away than theta, or whatever your threshold is, then I'm not going to worry about computing the gravitational effects for every single planet. I will just use the center of mass and use that as a generalization of all of the bodies that come underneath that section of the tree. And therefore, I don't have to traverse all the way down the leaves. I don't have to compute all of the individual forces. I can compute one force for that entire section of planets based on that one center of mass, saving us a huge, huge, huge amount of computation effort. So, let's talk about parallelization. The force computations are the ones that are usually dominating the runtime. So those are the ones that we really want to try and parallelize. Particle advancement is very easily parallelizable. Once we know the velocities, it's very easy to go to each of the bodies and say, hey, move forward 10 seconds of time based on whatever algorithm you want, Euler or midpoint or bunch cut or whatever. So that's easily parallelizable, but we can also parallelize making the tree. Trees have a nice recursive structure, so I can easily, as I'm constructing that tree, once I get past a certain point, I can spawn processes to do certain subsections of the tree, which is a nice thing to be able to do, right? There are some issues when it comes to parallelization. So the concept seen here for tiling the tree, what this is trying to do, consider that when I am traversing the tree for one of the bodies, trying to figure out where it's going to go next, if I have another body that is very close to it, that body's tree traversal is going to be very similar, right? It's going to follow a very similar path, and maybe right at the very end, it'll diverge a little bit. But for the first so many levels, they're following basically the same path through the tree. So why not try and reduce the number of times I have to trace that same path? What tiling the tree does is it says, okay, instead of computing the forces for one body and traversing the tree for one body at a time, I'm going to try and group these planets together by group planets that are close together in a single unit, traverse the tree once, not just for one planet, for all of those planets that are close together in physical space, so that they can reuse, we can actually just traverse the tree once, and then as we go down the tree, as we hit splits, well, okay, we can then split off at that moment in time, right, and traverse the last few steps of the tree individually if we need to, but at least we don't have to recreate all of the first steps that are at the top of the tree. These are going to be very big trees, by the way, right? We're talking about tens of thousands, millions of bodies we're talking about. So any time that we can save in that tree traversal is going to be worth it. The other thing that's interesting to think about when it comes to parallelizing this particular algorithm is load balancing. So as we saw like on the graph, for example, if I'm trying to parallelize this, well, if I am responsible, if we just take a very simple case, say I'm going to break it up into 4 different processes, each with its own quadrant, you can see that, well, okay, these 2 quadrants look like they're probably going to have most of the work, whereas these 2 quadrants down don't have nearly as many bodies. So they're going to have less work. So how do we try and balance that out? The technique that Barnes-Hut uses to try and get around this is called cost zones. So what it's going to do as it traverses the tree, it's going to record the number of computations that are performed for that particular node of the tree. So as I pass through, or as I traverse down the tree, I get to the leaf node and I do whatever force computations I need to, it'll record the number of computations that I needed to do on levels higher up on the tree, so that on future iterations, we can then use those number of computations in the tree to determine how we're going to split up the work across our processes. So we're actually using, we're adapting our algorithm as we go based off of how much work we've done in the past. That will help me determine how I'm going to split up the load in the future. That's the idea of cost zones. All of that put together, I think I already talked about the point-to-point method. That's big O of n squared. Barnes-Hut, bringing the tree into things and all of the other optimizations I talked about, gets us to a much cozier n log n runtime, which is a big difference, right? Especially when we're talking about very, 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 very large values of n. So even though we're going to be using the less efficient algorithm, we're going to be doing the n squared version homework assignments, Farnside is such a classic example. I would feel bad not covering it when talking about the n-body problem. But now that we've got all that out of the way, let's spend the remaining time that we have talking about the fourth homework assignment. It is an n-body simulation. I'm going to show you how to run it in a couple of different ways. So everything that I did with the previous MPI examples, as I mentioned before, they were run on a single machine, which is not really what MPI is intended for, right? MPI is intended to be run across lots of different machines. I want to show you how to do it both ways. I'll show you how to run it locally on one machine, which can be useful, but I also want to show you how to run it across multiple different machines, which requires accessing the Linux lab machines in a different way than we've done on previous homework assignments. So I'd really, I think it's probably in your best interest to make sure that you know how to do this before you leave here today. Of course, I'm happy to help you if you run into problems on the homework assignment, but part of the reason that I'm doing this is to make sure that you're prepared to work on this assignment. So first things first, we got to go grab the code, and I'll go through the write-up in a little bit as well once I spend some time showing the code to you. The write-up is a little bit different this time as well. Just a little bit. This is also a bigger program. The programs, I would say, have been kind of increasing in complexity as we've gone over time, and this one is by far the most complex of the homework assignments in terms of the code that you're being given. Just kind of a fair warning. All right, let me get back to my terminal here. So I downloaded the code and I extracted it, and now I'm going to navigate to the directory. Let me, I have two terminals open. I feel like I might have two terminals open. That's okay. So here I am in the homework 4 directory, and as promised, you can already tell before we even take a look at the code that it's more complex because there's a lot of different files this time. Some of these files are pretty short and sweet. The ones that I think are probably, the most interesting to you for the homework assignment are this Galaxy file and this derivs client file and derivs, I think, are probably also ones that are interesting to look at. You are, of course, welcome and encouraged to look at all of them, but some of them are less interest to you than others. Let's take a brief tour through the code, and then I'll show you how to run this. This is the entry point. So this is where the main method is. So this is where everything gets set up. And you can see, just like we saw in past examples, that we're taking a look at we have some stuff that's only being run by the main thread. We kind of have a client-server setup going on here where the main thread acts as the server, and then all of the the main process acts as the server, and all of the other processes acts as clients reporting data back to the server process, which aggregates all the data and presents the results. So you can see that there are timing things up here. So MPI has its own timing calls. If you want to use these timing calls on the report as your metrics, that's totally fine with me. That's completely reasonable thing to do. Here you can see right off the bat, we're sending out some information to all of the different processes, basically just telling them, go ahead and get your work started, everybody. And then we have a bunch of different arguments. I'll explain what the arguments are when I run this thing a little bit. One thing that's interesting to note about this program, there's a display involved. I'll show you, there's actually graphics. You can actually see the bodies moving over space, which is kind of cool. I want to make it clear, though, that for the purposes of the assignment, I don't care about that. I don't care about the performance of actually drawing the bodies. I just care about the computations themselves. So if you're analyzing the performance of this program, if you're working on the homework assignment, don't try and focus too much on the graphical side of things. That's mostly, I would say, for debugging purposes, to make sure that it's working properly. Not a focus of this program at all. In my particular opinion. But so this stuff is all display. This stuff is all just setting up the window and drawing the bodies and things like that. Making image, same story, setting up everything. But this is where we get to more interesting stuff. Run step. You can see, oh, hey, there's methods for, there's the Euler method right there. And then here's one for I Euler, which is the what I was calling the midpoint method. I think it's for like a intermediate Euler or something like that. But that's equivalent to the midpoint method. And then we have one down here for Runge-Kutta as well. So all three of those options are included and will give us varying degrees of accuracy of the model, as I was talking about. Um, Here's all the code down here for the client side. So this is where a big chunk of the work is going to be happening. We're waiting for a message from the server, the main process, to tell us whether we need to do some work or not. And then based on the message that we receive, we will call a method in a different file. So this is all kind of admin / graphical stuff. There is some stuff in here that's of use to you. So I would say the run server function is of interest. The main function, of course, is of interest. And then also, as we get down here, run step and run client are of interest to you. A lot of the other stuff in this file, I would say, is not of interest to you. So let's go over to the derivs client file next, because this is where I believe it's going to be doing a lot of the force computations. So here we are receiving messages from the server with the number of points per CPU. So how many points am I responsible for? G norm is gravity, I think, because you can adjust, various parameters regarding the physics, the mass. The shield radius is the shield radius is a threshold, basically saying that if two bodies are so close together, right, then they can essentially be treated as one. So this is a slight optimization. If I have two bodies that are within the shield radius of one another, then I'm basically going to ignore them, treat them as the same for all intents and purposes. That's what the shield radius represents. And then what is this final one? Just the very well named variable called x. I love it. What is that one? I also love this comment. Do stuff. Yes, very helpful. What stuff are we doing? Well, this is all the physics down here. So you can see we're computing differential equations. Be very careful if and when you decide to get into this very mathy part. This is where all the physics is happening. This is where we're computing the velocities based on gravitational effects. You can see we're inside of a double for loop here. So this is for each of the values on our particular CPU, and then for all of the points, right, for all of the actual bodies. So we're comparing all of the bodies that we care about against all of the bodies in the entire simulation. That's what these two loops represent. Do a bunch of physics, do a bunch of math, et cetera, et cetera, et cetera, and then send the data back to the main server so that we can, the main server process so that we can update our simulation results and get ready for the next round. So this is where all the math is happening. I'm not too concerned about the math, right? The math is what it is. This isn't a physics class. That's not the part that I'm most concerned about. I'm most concerned about all of the sending and receiving and communication stuff that has to happen. So let's try it out. I know I haven't shown you all the code. I'm going to let you, dig through some of the rest of the code. I've tried to show you the most important points of the code. First, I'm going to run this locally, just like we did with all the previous examples. So in order to do that, I'm going to go ahead and make it. Oh, whoops. I need to do module add tau MPI, and then I can hopefully run make. Yeah, there we go. It does spit out some warnings, but these are just warnings, so it didn't actually fail. It just complained about a few things and then compiled it anyway. So that's okay. You can see that the executable is called nbody. Now you can't execute it. There's arguments involved, and I actually don't really remember what the arguments are, so I need to look them up, which I can do on the website here by pulling up the assignment page, because the assignment page tells us what the arguments are. So if I scroll down to this section, you can see the first argument is how many bodies, the number of stars. The second one is the mass. How? So we are taking some simplifications here. Of course, not all stars have the same mass, but for the purposes of this problem, they do. And then how many time steps do we want? 1,000 time steps. And then this last one is a little bit interesting. This indicates whether we want to see the simulation or not. So for the purposes of this homework assignment, we don't have to, you can keep it at 0 and do the whole homework. You don't ever have to actually look at it, but it's kind of cool. So I would like to at least show it to you and show you what is actually happening, show you what it looks like. It is very useful for debugging purposes, right? If you make some changes to the code and then run the simulation again and see that it's doing way different stuff and the bodies are moving in weird ways, then you know you broke something, right? So just an easy and quick check to make sure that the code is actually functioning properly versus the way it was originally given to you. So 124 stars with a mass of 200, 1,000 time steps, or maybe I'll make it 10,000 time steps just because I think 1,000 is not too many. And then I'm going to turn the display on. Oh, and actually I did this wrong because this is an MPI program, so I have to say MPI exec up here. I almost messed that part up. Let's give it a go. Uh-oh. What did I do wrong? Oh, what did I do wrong? I got this to work earlier today, but I did have a little bit of trouble with it. Assertion to, oh, I actually saw this earlier today. What did I do to fix this problem earlier today? Do I need to specify, probably 4 processes? Does that help? Nope, that does not help. Mm, This this is telling me that it can't open up the window. I believe if I ran it without the display, it would actually no, it's still hmm. Did I get one of the arguments wrong? Let me double check. I promise I had this working earlier today. I cannot remember what I did to fix this particular issue. Well, shoot. That's kind of anticlimactic, isn't it? Um, Well, this is a direct terminal to the Linux Lab machine, so it should be able to access the same display that it's using to display the machine to me on the tab. I definitely had the display up and running earlier. I am just trying to remember how I had it up and running earlier, because I did have to do something a little different to get it to work, and I don't remember what it was off the top of my head. I should have written it down. Hmm. Um, I'm sorry? I'm sorry? Maybe so. That's actually a good idea. Um, so here, yeah, you can see this is where I was trying to run it before. I did a make clean and a make on it. But I already did that, so I don't know why that would make a difference. And then, oh, I just ran it directly. I didn't actually use MPI exec. That's interesting. Did that actually, let's try it. Oh, whoop. Oh, lowercase, lowercase b. Hooray! Oh yeah, that works. So, okay, let me make it a little longer because it was pretty fast. Achoo. So there it is, simulating all the bodies in space. Cool. And you can see that it starts it off as a kind of a spherical simulation. Um, there's tons of options in this program. If you dig into the code, you'll find other options. You don't have to start it out as a sphere if you don't want to. There's other shapes and stuff you can kind of play around with. But as I mentioned, this is more of just a sanity check than anything else. It's a little disappointing that I couldn't run it using MPI exec though, because that means that it was just being run serially, right? Which I'm a little bit confused about, to be honest with you. But it did work, so yeah. I'm not going to worry too much about it because I want to make sure to cover the important bits. Um, you definitely can run it locally. I showed you how to do that, although MPI exec isn't quite working, so that's a little bit confusing. Uh, That's okay though, because the more preferred approach is not that, right? I'm not as concerned with whether you can actually open up the window and see it. It's fun. It's fun to play around with, but that's not really what I'm concerned about. I'm more concerned about you being able to run this on multiple different machines. So running it on one machine is fine, and I'm not saying you shouldn't do that. I think you certainly can run it on a single box and use that as part of your analysis. But the homework write-up, which I'm going to show you and talk to you about here in just a second, specifically asks you to focus on what happens when it's running on multiple different machines. And so in order to do that, we have to run it on the cluster. We have to submit a job using Slurm. We have Slurm set up on our own cluster. Talked about Slurm quite a few times over the course of the semester. So we have to use Slurm to run this on the cluster if we want to actually have it be spread out across multiple different boxes. In order to help you out with that, I gave you this script called mpi.sh, but you will have to make some changes to this script in order to do what you want to do. The first thing that you'll notice is that down here, there's a couple of paths that aren't set because these paths are going to be different for all of them, right? They're probably going to have your username in there. So the first thing that you have to do is you actually have to compile the program using the makefile yourself. So compile the program and then make sure you change these paths to be the actual location of where the homework is, which if you need a little refresher, the pwd command will help you out here because it tells you the full complete path, absolute path to the directory that you're in. So yours will probably look pretty similar to this. And if I wanted, and I want to try this out, so I'm actually going to fix this up right now. Edit this path in home, compute, dshook, downloads, and then same thing down here. Home, compute, dshook, downloads. So you will have to edit this script to make sure you have the correct path set. Notice that this is the call to the actual executable itself. So if you need to change any of the arguments, now you do not want the display to ever be 1 on the cluster. It won't work. It'll crash. So please make sure that final argument, if you're running this on the cluster, is always 0. Otherwise, you'll run into problems. But the first 3, you are certainly welcome to change and modify and may have to analyze the performance of this program. Let's real quick come up here to the top, though, and talk about what all this SBatch stuff is, because that's important, too. Some of it I think you can kind of figure out just based off of the stuff that we've done in prior classes. You can see that this is the Linux lab machines that we're talking about. This is the name of your job. So it might be a good idea to, stick your name or your WSL key on there just so you know that it's labeled properly with yours. This is the directory where the output will be. So I'll show you that in a little bit. You probably don't need to mess with that though. The ones up here at the top, these are important. So this is quite literally saying how many physical boxes do you want? That's the first one. So right now I just have it set to be one, which means it's all going to run on a single machine. If you actually want it to be spread out across different machines, you can change that to two or more. I'm not sure how many actual physical boxes are on the cluster, so I don't know what the maximum number is there for number of nodes, but maybe one of you will find out the hard way as you're playing around on this. And then this is the number of tasks per node. So how many processes do I want to launch on each? And then the one below that is the total number of tasks. So obviously these need to match up. This number times this number needs to be this number, right? In order for it all to logically make sense. So as just one example, if I wanted to launch this on two boxes with four processes per node, I could do something like this, right? Just change those values accordingly. If I wanted to have four boxes with, 8 processes per node, I can do that, but then this needs to be 32 to correspond to the fact that I now am going to have 32 processes running at the same time, for example. This value down here, please do not change this one. It's an interesting one to think about because this is saying how many what is this saying? How many CPU cores we want per process. So if I change this to be anything other than one, right? Even if I change this to be two, I am now requesting 2 CPU cores per process for a total of 64 cores, right? Because I have 32 processes listed for tasks. So please keep that at one. Think about why you might want to change this, though. I sort of hinted at this a little bit earlier throughout the day. If I was using OpenMP in addition to MP, then it would be great to change this to be something other than one. Then I could have one process spin up that has 4 cores, and then use OpenMP to spawn 4 threads that execute all within that one process. So that's how you mix and match right there. But we're not doing that. We're not doing OpenMP. We're not mixing the two paradigms together. So that should always be one. Leave that always at one. But the ones up top, you can definitely fiddle around with. You can definitely change if you want to, and you should, right, in order to answer the questions that I'm going to ask you to answer on the process. But let's actually try it out. I'm a little nervous that this is maybe a bit too much, so I'm going to scale it back a little bit just so I don't get yelled at by IT. I'll do eight processes on 2 boxes for a total of 16 tasks. That seems fairly reasonable. Now, I think I already mentioned this, but I'm going to mention it again. You have to compile the program first. So make sure you have the executable first. The script does not compile your code for you. So run make ahead of time. Get your script looking however you want your script to look. And then to actually run it, you have to do sbatch mpi.sh. It will read all those variables in. Slurm will set up the environment, get everything ready for you, run the code, and then provide the output to you. Now, I'm a little actually nervous that this may not work. We'll see if it actually runs. Yeah. I'm a little nervous that it's not actually going to work, but we'll see. It did at least submit it, and now you'll notice that I have this directory here called run outputs. That's where, of course, the outputs are going to go. And then it tells me the job number. So the output is going to be in the file with the job number on it. So if I then cat this, take a look, yeah, this did not work. I got an error. I got all these weird error messages. This is not what it's supposed to look like. So I was actually kind of expecting this. Is what I ran into earlier. But this is where things are a little iffy with these Linux lab machines. It actually does not want you, the way that IT has this set up, it does not want you to submit bash scripts directly from one of the Linux lab machines. It really wants you to submit it from shell. So this is a case where using the visual interface is maybe not the best way to go. You can, of course, SSH into shell from here, though, which is what I'm going to do now. Oh, that's not right. So if you're going to run the script using sbatch, you have to SSH into shell. There's no negotiation about it. You don't have to do it through the visual interface. You can do it directly from your computer if you want to. That's totally fine. But you have to do it from shell. That was the that was the lesson that I learned earlier today. The good thing is that the file system is set up the same. So, I already actually compiled it and stuff on this Linux lab machine. So if I navigate into the directory, I'll see that, oh, hey, it's still, the executable is still there. The output directory is still there. The script is still there. So, I should just be able to sbatch mpi.sh from here. And oh, okay, no error message that time. That's good news. And now, once the job is done, which these jobs don't typically take very long to do, fortunately, we can come in here and, oops, open up the 6. Number of nodes is 16, and there's the wall clock time. That's all it's going to do, right? That's all the information we get. That's all the information we need. If you don't mess with the mathy stuff, right? You can assume that the computations are correct. Some of you may want to go in and mess with the mathy stuff. That is a potential option. I would just encourage you to be very careful because I've certainly had students in the past on this problem, on this homework assignment say something like, "Oh, hey, I made this change and everything worked a lot better after that," but like you totally broke all the math and stuff. So that doesn't really that's not a very good finding if it doesn't work anymore, right? So be very, very careful. With all that in mind, I think now's a good time to talk about the actual assignment itself because it is a little bit different than past assignments because I am kind of taking the choose your own adventure part away. There are 3 prompts. Everybody has to do these 3 prompts. You can still work in mind, you still work together with a partner if you want to, but everybody's doing the exact same 3 prompts. What's the performance depending on the size of the problem here? And size of the problem, don't just limit that to n. N is one factor, yes, size of the problem. I'm not disagreeing with that. But as you dig into the code, you'll notice there are lots of other things that you could tweak in there as well, some of which have an effect on the performance, some of which don't. So I would like for you to at least, yes, do n. Obviously, that is an important one, but also pick at least 1 or 2 of these other parameters that you can tweak for the problem and see how that affects the performance as well. I'd like for everybody to do that for that particular part. And then number 2, that's kind of what we were just talking about. How does it perform as the number of nodes is varied, especially if you're using more than, it says here more than 16 cores per node. I don't know that that's entirely accurate though, because you can, as I just showed you, force it to spread out across. In the past, the way that the cluster was set up, it would only give you multiple boxes if I requested more cores than were on a single box. That's not true anymore, though. I just showed you the MPI script. I can force it to operate across multiple boxes, even if I request fewer than 16 cores, which I think is how many cores is on a single box. So don't worry too much about the 16 cores per node part. Definitely, though, make sure you're running it across multiple boxes. Communication is an important part of this program. So I don't think any answer to this problem is going to be sufficient if it's run on a single node. Please scale it up to 2 or even 3 or 4 nodes, right? Or even more than, I don't know how many nodes there are, but maybe some of you will be curious and try and push it and see how many nodes you can get away with. Definitely scale it up and use that as part of your analysis. And then number 3, hopefully a fun one, I want you to improve the performance of this program. There are lots of ways to do this. This program is not the best written program in the world, and that's somewhat intentional, right? I wouldn't, if it was already optimized to heck, then this would be an impossible task. So I think the fact that it does have a little bit of rough edges is helpful in this regard. I'm not looking for the biggest performance improvement in the world. If you can demonstrate any kind of performance improvement to me, that is fine with me. But I definitely need to see that comparison. Here's how it ran before I changed the code. Here's how well it ran after I changed the code. And please, 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 please give me a screenshot or copy paste the actual changes that you made. I don't need the whole files, right? I just need what you changed. So if you change 3 lines, I just need to see those 3 lines and know where those 3 lines were changed. I don't need all the files again. Just put the actual code snippet that you changed in your report so that I have that to reference. Make sense? Any questions? Everybody kind of feel like you know what's going on? I know some of you are probably still in homework 3 mode, not even ready to think about this problem yet. That's totally fine. But yeah, please let me know if you do have any questions. I'm, of course, available by email or whatever the easiest communication way is. And that's it. That's all I've got for you today. We're about out of time anyway. It's almost 8 o'clock. So go ahead and wrap it up here. If anybody has any questions about homework 3 or want to chat about anything else before you leave, I'd be happy to do that. Otherwise, have a great weekend, everyone, and I'll see you back here on Monday.